Hello, I'm Cameron Smurl, and today we have our third screencast video for differential equations. And today we'll be solving second order differential equations using the Laplace method. Here I'll quickly go over the steps. First, we need to take the Laplace transform of the entire function that we're given, or the entire equation. Second, we need to solve for the unknown, which is just simple algebra. And third, we need to take the inverse Laplace transform of that equation. And we'll do this by using partial fractions. Here's a few formulas that I thought were useful when I was solving this equation. The Laplace of the unit step of t is equal to 1 over s. The Laplace of delta of t minus a is equal to e to the minus as. And the inverse Laplace of a over s squared plus a squared is equal to sine at. All right, so we'll get right into the problem. We have y double prime plus 16y is equal to the unit step of t minus delta of t minus 1. And y of 0 is equal to 0, and y prime 0 is equal to 1. The first step, we need to take the Laplace of the entire equation. So this entire thing right here. So by doing this, I'm just going to take the Laplace of each individual portion of this equation. So we have the Laplace of y double prime plus the Laplace of 16y is equal to the Laplace of unit step of t minus the Laplace of delta of t minus 1. Okay, so first we'll do y double prime. So the Laplace of y double prime is equal to s squared of the Laplace of y minus s times y of 0, which is equal to 0. So that'll cancel, minus y prime of 0, which is equal to 1. So simplifying and canceling things out, we get s squared times capital Y of s minus 1. And for the rest of the time, I'll refer to y of s is equal to the Laplace of y, just to save a little time. Next, we take the Laplace of 16y. We can't really do anything. That's why we're solving this equation. But you can pull out the 16 in that. So you have 16 times y of s. Next, we'll take the Laplace of unit step of t, and that's equal to 1 over s. And lastly, we'll take the Laplace of delta of t minus 1. And from our formula before, this a right here is 1. So our equation is e to the negative s. Or the Laplace of delta of t minus 1 is e to the negative s. Okay, so once you put everything together, you get s squared plus 16 times y of s minus 1 is equal to 1 over s minus e to the negative s. Second step is just solve for y of s, and that gives you 1 over s minus e to the negative s plus 1 over s squared plus 16. Then I just distributed this s squared plus 16 to all three of these, and this is what you get. Third step is you take the inverse Laplace of y of s. So you can just take the inverse Laplace of each different section of this equation right here. And we're going to start off with these two at the end because these are simpler. We're going to start off with this middle one right here. So we take the inverse Laplace of e to the negative as of f of s. Oh yeah, this is the general form. So the inverse Laplace of e to the negative as times a function s is equal to unit step of t minus a times the function, or f of t minus a, where u of t is the heavy side step function. So I just split this right here up, the e to the negative s over s squared plus 16, into the inverse Laplace of e to the negative s times the inverse Laplace of 1 over s squared plus 16. The inverse Laplace of e to the negative s is u unit step of t minus 1. And from that equation earlier that I showed, the inverse Laplace of 1 over s squared plus 16 is 1 over 4 sine 4t. And the reason why we get this 1 over 4 right here is because this top number, this 1 right here, needs to be a 4, since it's a over s squared plus a squared in the formula. And you cancel out that 4 by putting a 1 over 4 right here. And then you put those two together, you have the unit step of t minus 1 times 1 over 4 sine 4. Yeah. 1 over 4 sine 4 times t minus 1. The next one, we already did this inverse Laplace right here. You have the inverse Laplace of 1 over s squared plus 16. That gives you 1 over 4 sine 4t. Lastly, we have to take the inverse Laplace of 1 over s cubed plus 16s, and You do this via partial fractions, and that comes out to 1 over 16s minus s over 16 times s squared plus 16. So we'll take the inverse Laplace of 1 over 16s first, and that comes out to 1 over 16. Next, we'll take the inverse Laplace of s over 16 times s squared plus 16, and that pull out the 1 over 16. Then we can just take the inverse Laplace of s over s squared plus 16. And there's this theorem for the inverse transform rule, where the inverse Laplace of s times a function s is equal to the derivative of the inverse Laplace of this function plus f of 0. So we can just do that, pull out the s, take the inverse Laplace 1 over s squared plus 16. Luckily, we've already done that. And that gives us 1 over 4 times sine 4t. Next, we're going to take the derivative of this function, and that comes out to cosine 4t. Now we put it all together, and we have the inverse Laplace of 1 over s cubed plus 16s is 1 over 16 minus 1 over 16 cosine 4t. And you can just kind of simplify it a little bit. You have 1 over 16 times 1 minus cosine 4t. And we can put all three of these parts, this one right here, this part, and this part together, and that gives us our y. So we have 1 over 16 times 1 minus cosine 4t minus unit step t minus 1 times 1 over 4 sine of 4 times t minus 1 plus 1 over 4 sine 4t. Lastly, we can just simplify this a little bit. This unit step of t minus 1 is equal to 0 when t is greater than or equal to 1. So that cancels out for t is less than 1. So this part right here cancels out, and you're left with 1 over 16 times 1 minus cosine 4t plus 1 over 4 sine 4t. And when t is greater than or equal to 1, y is equal to 0. Pretty sure that's it. Thank you.